Now we're skipping on to example 8, which is a different type of problem with the language that kind of signifies it is this idea of cross sections that are perpendicular to the axis, in this case the x-axis. So what that means is, I'll do the best I can, you've got really a three-dimensional object that's not coming from rotating it, but it's coming from shapes coming out from the grid. So in our first example, we'll do a rough sketch. The base or the bottom of our object is a circle with a radius 5. So this would be the bottom of the object. And part A tells us that the top of the object is a bunch of squares. So that means coming out at you, this is going to be a really bad drawing, I think, are just shapes, tons of squares. There's one square, here's a different square, here's another square. It's really hard to draw here. If I could look at this from the side, you might see something like this. So this would be maybe the very middle of the object, and then it's going to have square shapes coming at you the whole way. They're probably getting smaller because the circle, in terms of its distance apart from edge to edge, the chords of the circle are shrinking, right? They're largest at the middle, at the diameter, right? And it's going to keep shrinking down squares until you get to just a single point. Right? So that might be the side of the object. The important thing to recognize is that you have slices of a certain shape, and if you could find the area of all of those slices and add them up, then you could talk about the volume of the entire object. So let's do some practice here. So again, in this example, we have a circle that is a base of some solid object, and this circle has this equation, which means it's centered at the origin, and its radius is 5. So we've got a base of an object that's doing something like this. It's not a great circle, but it's good enough. And the cross sections that are coming out at us are all squares, which means what we're going to integrate in this case is an expression for the area of our squares. And we know that the area of a square is just side length squared. And since they're perpendicular to the x-axis, all of our squares are going to go from -5 to 5. From left to right, from -5 to 5 would be all of our squares. All of them have different areas, but the sum of all of their areas would be the volume of that entire object. Maybe it's a funny looking snow globe, might be another way to think about it. What we need then is an expression for this distance right here, because that distance would be the side length of a square. So what we do know is that the whole square is x squared plus y squared equals 25. If we were to solve this particular thing for y, which we've been doing for years now, what we get is y equals plus or minus the square root of 25 minus x squared. And the thing to recognize is that the top portion from the axis up would be the positive root, and the bottom portion from the axis down would be the negative root. Right. Now, since the circle is symmetrical, I'm not going to overthink this. I'm simply going to look at what is the volume of this portion and double it. So I am looking at a square. Well, no, I won't do that. Let's just do the whole side length here. So what's an expression for this distance? How do we express that? well, hopefully you saw that entire side length would just be 2 times the square root of 25 minus x squared. Half of it would go up and the other half would go down. So that's our side length. Which means then we can integrate from negative 5 to 5 our side squared. So that would be 2 times the square root of 25 minus x squared squared dx. And there's some other things that we can do. I'm trying to keep this as simple as possible. If we clean this up just a little bit by squaring it, we end up with 4 times 25 minus x squared, or 100 minus 4x squared dx. And that's not really a big deal for us to integrate. When we integrate this, we end up with, oops, should be a bracket, 100x minus 4/3 x cubed. We'll be evaluating it from negative 5 to 5. Let's start with our upper limit of integration. So this will be 500 minus, what's that? 125 times 4 minus 500 over 3 minus, when we put in negative 5, this will be negative 500 plus 500 over 3. And so all together we end up with 1,000 cubic units, because it's a volume. And again, the reason there's no pi is because our shapes were all squares, so we integrated an expression for the area of a square. Part B of this we'll do in a moment. We're looking at equilateral triangles instead of squares. So that means that coming out at us are shapes that are equilateral triangles instead of squares. And we'll need to find expression for areas of those squares. Now the bottom of our equilateral triangle is what's going across this distance right here. We already know from the last problem that that is 2 times the square root of 25 minus x squared. What we don't know, and what we need to know though, is the height of this square. We don't know the height of this. And we need to know the height so that we can find the area of our object. So think through, how is it that you're going to find the height of this object? Hopefully you thought the Pythagorean theorem, right? Our hypotenuse, since it's equilateral, will be 2 times the square root of 25 minus x squared. That's our hypotenuse, so we'll need to square that. And that needs to be equal to what we want to know, our height squared, plus the square root of 25 minus x squared squared, right? Because the whole thing is 2, the height will cut it in half, cut our base in half. When we begin to solve for h, this is what? 4 times 100, I'm sorry, 4 times 25 minus x squared minus 1 of 25 minus x squared. So h squared is 3 times 25 minus x squared, or the height itself is the square root of that. So now we have an expression for our base and an expression for our height. So we know we have a way to set up our integral, because again we're just going to integrate the area of our equilateral triangles. Our triangles in terms of x go from negative 5 to 5, and the area of an equilateral triangle is 1/2 the base, which we said is 2, times the square root of 25 minus x squared times the height, which we said is the square root of 3 times the square root of 25 minus x squared dx. I'm going to clean this up a little bit. So we'll have the integral from negative 5 to 5. The square roots will cancel each other out and free up the 25 minus x squared. 1/2 times 2 is 1 times the square root of 3, so I'm going to pull that constant out and integrate everything with respect to dx. When I integrate, I'll have the square root of 3 times 25x minus 1/3 x cubed from negative 5 to 5. Plugging in my upper limit, which is 5, we end up with 125 minus 125 over 3 minus, plugging in my lower limit, I get negative 125 plus 125 over 3. I don't want to forget my root 3 when I combine everything. This ends up being 250 root 3 units cubed for volume. Let's do 2 more examples of this. The shapes are different. This time we've got semicircles. So in our semicircles, it means that the objects that are stacked from left to right are all semicircles. And I'll put in the base of our semicircle in red. It's going from here to there. So what we know is this portion, which is the diameter of our circle, and half of that would be the radius. So we know the whole thing, again from previous work, is 2 times the square root of 25 minus x squared. So the radius of our circle must be half of that, or 25 minus x squared. Right, that's just an expression for the radius everywhere. The area of a semicircle, the area of a circle is pi r squared. If you divide that by 2, you have the area of a semicircle, because it's just half of a circle. So that's what we need to integrate. And again, from negative 5 to 5. Now, one thing that we can do to make some of these calculations perhaps easier is integrate from 0 to 5. Because if we just integrate from 0 to 5, because of the symmetry of the object, we'll have half of the volume, and if we double it, we'll have the whole volume. So we'll do it this way, and integrate from 0 to 5, and I have to remember to multiply it by 2. The area formula for a semicircle is 1/2 pi, and r squared in this case, well, r is 25 minus x squared. It's the square root of that, and we're squaring it, dx. Clean this up, this will be pi times the integral from 0 to 5. If you're wondering where the 2 went, 2 times 1/2 is 1. And I'm just integrating 25 minus x squared, because I squared the square root. Integrating, this works out very nice. We've got 25x minus 1/3 x cubed. And since I integrated it, this shouldn't be here. But I will evaluate it from 0 to 5. When we plug 5 in, we get 125 minus 125 over 3. And cleaning that up a bit, since I'll have 2/3 of 125 left, then that means there will be 250 pi over 3 units cubed for my volume. The last shape we need to deal with here are isosceles right triangles. So an isosceles right triangle means that these two legs will be the same length. This must be a right angle, and this is the hypotenuse. Those are the shapes that are stacked horizontally, and that means that our familiar piece going across the circle is the bottom of our isosceles right triangle. And again, that piece was 2 times the square root of 25 minus x squared. Now if we remember some facts about our 45, 45, 90 triangle, we know that if we just divide this piece by the square root of 2, we'll know what this length is. Right? So L, because of our 45, 45, 90 relationship, has this value to it. And so we'll be able to use all of those facts to come up with the height of our triangle. The other thing that we could recognize is that this triangle, if we just turned it, would look something like this. So if we just flipped it onto its right angle, this is our triangle. So this is our length that we had. Here's the length. Here is our hypotenuse. And what's good about that is now L times half would give us the area of this. So if we use that fact, just by thinking about it a little bit with our geometry, we still need to integrate an expression for the area of our triangle, but we're going to look at it as that quantity squared, right? So the area would be 1/2 times 2 times the square root of 25 minus x squared over root 2 squared dx. Right, so again, we're just using some geometry here. If I clean this up just a little bit to make my integration a little bit easier, this ends up being 1/2 times 2 is just 1. I square all of these things, I end up with 25 over 2 minus x squared over 2 dx. So now the integral is not so bad, from -5 to 5. Since I'm integrating, I don't need this, I just need brackets. I'll have 25 over 2x minus, let's see, it's going to be 1/6 x cubed from -5 to 5. Substituting in 5, what will that be? That'll be 125 over 2 minus 125 over 6. Now I just need to substitute in -5. So it'll be -125 over 2 plus 125 over 6. And cleaning everything up, we end up with 125 cubic units for our volume. So there are cross sections perpendicular to the x-axis, right? So we're changing the shape, which changes the formula that we need to integrate.